Finally, we get to talk about electronic configurations, and some of you may have seen this. For some of you, the way I'm going to present it is going to be completely new, but hopefully, the way you're about to see it will give you kind of like the full picture of what the periodic table is trying to tell you all along. And in the next lecture, in fact, we're going to use that entire knowledge to derive values that maybe up until this point you thought you were supposed to be given a table or the values themselves to solve problems. We're actually going to calculating just by looking at the periodic table. So there's a lot of power to this. Okay, so let's first start by describing the periodic table based on the knowledge of the quantum numbers themselves. First things first, let's take a look at the periods or the rows. In the past, I've used the row number to determine the charges of anions, but there's actually a lot more to the row numbers than meets the eye. And specifically is the fact that the row number, technically speaking, represents the principal quantum number of the elements themselves. And specifically up to what maximum principal quantum number the element can have. So the row numbers cannot stand for that. And the interesting thing about it is that if you actually look at the periodic table, and now I'm highlighting it in terms of groups, if you look at it from the point of view that certain blocks in the periodic table are going to have specific orbitals associated with them, at least for the most outwardly, the valence electrons, then the picture arises in the following way. First, groups 1 and 2 are known as the s block. And for this group of elements, the outmost orbital is the s orbital, hence the fact that this is called the s block. Moreover, the energy level of that s orbital correlates directly to the row number. So if you're dealing, for instance, with sodium, the specific orbital and energy level of that orbital that lies at the very last in the list is going to be the 3s orbital for sodium. Same thing for magnesium. Now in the case of the groups here in orange, all the way to the right past the transition metals, these are known as the p block elements. And as the name implies, the last orbital present in this type of elements is the p orbital. Now, much like the s orbital, the number in front of the p is literally the number of the row in which the element is located. So for oxygen, oxygen is in the second row. So the last orbital that it will contain will be the 2p orbital. Now another thing I want you to notice is that for the s block, we have two individual groups present. That's because the s orbital is only present as a single orbital for any given energy level. So you only have one type of s orbital for the first energy level or the second energy level or so on and so forth. But the s orbital can take up a total of 2 electrons, one with positive spin and one with negative spin. So together we have two groups, allocating for the fact that there is 2 electrons total that can be present in that s orbital. Looking at the p block, the p block has a total of 3 kinds of p orbitals, no matter which energy level you're in, but each one of those orbitals can take up 2 electrons. 3 times 2 means that you're going to have 1, 2, 3, 4, 5, 6 blocks as part of the p block. Similarly, the transition metals have d orbitals as the last orbital present in their series, and the d orbitals come in sets of 5. Each one of them can take up 2 electrons, so you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes in the d block. Now the caveat though here is that unlike the s block and the p block, the d block is associated not with the row number itself, but rather the row number minus 1. So row number minus 1 is going to be the number in front of the d for the given element. So for instance, looking at manganese, manganese is on the 4th row. That means that the d orbital of manganese is going to be not the 4d, but rather the 4 minus 1d, or in other words, 3d orbital. And lastly, for the f orbitals, if you count the blocks themselves, so excuse me, let's go back to this. If you count the blocks exactly, you're going to see that there's actually 15 blocks in this series. That's because when you look at the periodic table, there's this empty slot here for the transition metals, which is either meant for lanthanum or lutetium, or in the case of the seventh row, it's meant for either actinium or lawrencium, uh, but there's no real consensus as to which one of those goes in the actual table. So I personally like to say, okay, just go directly from barium to lanthanum and treat it as an F block element. Go directly from radium to actinium and treat actinium as an F block element. And by the time you get to ytterbium or nobelium, you will have completed the entire F block. And at that point, lutetium and lawrencium can be placed as the quote-unquote transition metals. But as I said, there is no consensus on that, right? It could either be like lanthanum or lutetium that is a transition metal, or actinium or lawrencium. That's kind of a technicality. For your purposes and what we're going to be doing here, I recommend that you use treat lanthanum and actinium as part of the F block and lutetium and lawrencium as part of the D block. That will kind of save you some hassle. However, one thing that needs to be said is that between barium and, in this case, if we go based on my premise, lutetium, we're going to have all of the F block preceding it. So right after barium, we start with the F block up until ytterbium, then we do lutetium, and we go back to the regular transition metals. And then for the seventh row, right after radium, we start with actinium, and we go all the way up to lawrencium. And in addition to that, make sure that when you're trying to come up with a notation, these F orbitals, the ones here starting with lanthanum up until lutetium, are technically in the sixth row. They're, we don't write them in here because otherwise the table will be rather long, but they're technically in the sixth row, and the ones here, actinium through lawrencium, are on the seventh row. As far as the notation goes, you subtract 2 from the row number to come up with the number in front of F. So in the case of cerium, cerium is on the sixth row. If you subtract 2 from 6, you get 4. The F orbital of cerium is none other than the 4F orbital. Alright, so this will kind of help you out a little bit. Now, what I'm going to show you is kind of cool, and it utilizes a periodic table to maybe not its fullest extent, but it utilizes it pretty well. And the idea is that we're going to write out the electron configurations for the elements by simply reading the periodic table the same way we read a book. We're going to start from the uppermost part. We're going to read it from left to right, and once we finish going through a column, we're going to move on to the next column. We're going to finish one row, and then we're going to move on to the next row, and we're going to read it from left to right, and we're going to do this until we reach the element for which we're trying to reach or come up with electron configuration. And like I said before, the row number is equal to the value of n for S and P block elements. The row number minus 1 is the number of n for D elements, and row number minus 2 is the number of n for F block elements. Alright, so I'm going to show you a few examples of how this goes. I'm going to start with something relatively simple. Okay, nitrogen. Let's say I ask you to write the electron configuration of nitrogen. Nitrogen is all over here, it's on the second row, and it's on the P block. But you got to start from the very beginning, and the very beginning is hydrogen. Also notice that I have brought helium all the way from the noble gases to here to kind of account for the fact that only the s orbital is going to be occupied on the first energy level. So we start with hydrogen. We say, okay, energy level is 1. We have 2 electrons because there's 2 boxes present in the s block. So we have an 1s2 present in the first row, and that's all we have in the first row. On the second row, we move on to the second energy level, and for the s block we have 2 electrons, so this is the 2s2 as I depicted right here, 2s2. And by the time we get to the P block, it only takes us 1, 2, and 3 blocks to reach nitrogen. Since this is the second energy level, this will be the 2p, and since it took 3 blocks to get to nitrogen, this will be the 2p3. And that's the configuration of nitrogen. I'm going to do one more. Sodium. If we look at sodium, we basically start from the beginning. We start with 1s2 for the 2 elements in row 1. Then we move on to the next row. We have 2s2. We move on to the P elements, and we have 6 of them, so that's 2p6. And at that point, we move on to sodium, which is on the next row. It's the very first element to the next row. So that will be 3s1. And this is 1 because we stopped at sodium. We didn't actually get to go up to magnesium. So the configuration will basically take you up to 3s1. Now I'm going to do a few more configurations to provide for further examples, but I'm going to save that for the next video since this one is already long as is. So I'll catch you in the next video.